Hey guys, how's it going? Professor Brian back. Another installment of Workout Wednesday. Still within nuclear chemistry, but I wanted to do a multi-part kind of large-scale application question that involved energy, mass, and kinetics, half-life, if you will. And this problem from the text was really interesting. 21.51 asks, it tells us that the energy from solar radiation falling on the Earth from the fusion that is happening in the sun is 1.07 times 10 to the 16th kilojoules per minute. And they ask us two questions. A, how much loss of mass from the sun occurs in one day from just the energy falling on the Earth? So we want to be able to convert a rate of energy to mass. And then part B asks us if the energy released in a nuclear reaction involving uranium-235, which is decaying via neutron bombardment, and we take that as typical of what we have in a nuclear power generator or reactor. What mass is required to equal 0.1% of the solar energy that falls on the Earth in one day? So we want to be able to compare what we can do in a nuclear chemistry reactor to what the sun is doing. So the first thing that we have to do is convert a rate of solar energy into a loss of mass. Okay, so what we would like to do first is write down the information that we have, kilojoules per minute. We want to know the mass loss in one day, and again, we're going to be using E equals mc squared and the constant for the speed of light. But what we must be able to first determine is total energy in one day, because that was what the question had given us. So total energy in one day is going to involve some dimensional analysis using the original rate, remembering that there are 60 minutes in 1 hour to convert to kilojoules per hour, and then that there are 24 hours in one day. So we end up with a value after we calculate of 1.5408 times 10 to the 19 kilojoules per day. And since we're dealing with one day, this value is the amount of energy in one day. So to determine delta M, all we do is manipulate our equation and solve for delta M in kilograms or grams or whatever. They didn't really give us a specified unit, so it can be any mass unit. So once we plug this in, we see that we end up with a unit of kilojoules second squared over meter squared. And remember, joules units is kilogram per meter squared over second squared. So it's the inverse of this, really. So we need to convert kilojoules into joules, and that's what I have done here. Notice I've already kind of crossed out some of the things, but if you can see, I have 1.712 times 10 to the 2, the answer, and I have the units listed here, and here I have the units of 1 times 10 to the 3 joules per 1 kilojoule. I wanted to get it back into joules because of this relationship. You can convert this multiple different ways, right? But this was the most straightforward. And then you see that 1 kilogram per meter squared second squared over joules is this relationship here. Is 1 to 1, right? 1 to 1. So once you look and see that everything crosses out, seconds, you're left with only kilograms. And really what that means is that this value here times 10 to the 3 is kilograms. All you had to do is convert back to joules, really, and then you get kilograms. So this is the value of kilograms. This is the answer that they're looking for. So essentially 171,000 kilograms is the mass change involved with that energy change. So focus here, again, the main focus here is to be able to recognize a rate, be able to convert that rate into total energy, and then be able to manipulate it using Einstein's equation. So second part B again asks us and gives us a nuclear reaction. Uranium with neutron gives us barium, krypton, and releases neutrons. They have given us nuclear mass for each of the reactants and the products. And they want to know how much mass of uranium do we need to equal 0.1% of the solar energy that we just calculated. So first thing I do always is write down the information that we know and that what the question is asking us. So we know we're working with uranium-235. We know we want to get 0.1% of the energy. So what I did was I calculated the energy in kilojoules, which we have up here, and looked at what is 0.1%, right? 0.1% is this ratio, and we end up with times 10 to the 17th. And here's the reaction, noticing that this is a question that is mass defect question, but you have to be able to recognize that where does the energy released come from in this particular reaction? It comes from the energy released as a product, and this is due to mass defect, due to mass change. And how can we calculate that mass change? Well, we need to look at the mass of the reactants, which are uranium-235 and 1 neutron, and then the mass of the products, which are barium-141, krypton-92, and 3 neutrons. So what I did was take the values that they gave us in the question and got a sum, a total mass for each side of our equation. And what you see here is that you got 236 on the reactant side and 235.8-ish on the product side. So we need to find the difference, and that difference is 1.910653 times 10 to the negative 1 AMU. This is an important value, right? This value here is delta M, right? This is delta M. And this is important to be able to plug into the equation of energy, right? The equation of energy per mass unit, right? So we had grams per mole here, which we can convert. And therefore, we need to just move this value into our energy equation, E equals delta MC squared. And we're going to be able to find the energy per mole, right? Energy per mole. So once we plug that in, we see we end up with grams per meter squared second to the negative 2 per mole. But we need kilograms to go into joules. So this is value, again, remember, this is equal to joules per mole. And then from there, I converted joules into kilojoules per mole, which gives us to this value. So all I did here was 3 conversions: grams to kilograms, kilograms to joules, and then kilojoules. So we got an order of magnitude of 3, right? Because we're in kilo. Now, if we know kilojoules per mole, we can also determine kilojoules per gram, right? Per gram. So we can do that using the AMUs associated with that particular isotope, right? 234.99. So now we know that there are 7.3175969 times 10 to the 7 kilojoules per gram of uranium in this particular reaction is released. So to get the mass necessary for the 0.1%, which we calculated, right, all we need to do is utilize a conversion using this ratio, which will leave us with units of grams, is to take this value and divide it by this value that we just calculated for kilojoules per gram of uranium, and you'll see that the mass of uranium we need is about 2.1 billion grams. So a huge amount, or about 2 million kilos. 2 million kilos to be able to produce the same, be able to produce only 0.1% of the energy associated with the sun. So this is a great multi-step application question that the reasoning and the thought process behind it, you need to be comfortable with come assessment time. Again, if you have any questions as it pertains to any of these problems or would like to see more problems, feel free to send me an email or make a comment, and I hope to look forward to hearing from you.